Welcome back. In this lecture, we will look at different efficiency metrics that can be utilized for characterizing the entire fuel cell system as well as its subcomponents. We can break down the entire fuel cell system into different subcomponents. For example, the first subcomponent can be schematically represented here in this manner. A fuel has its value because of its energy content. Not all of the fuel that is being utilized, that is being supplied, is being utilized. Based on the amount of fuel that is being utilized, you can denote something as fuel efficiency. We'll clarify these things quantitatively in the subsequent lectures. Then the fuel that is being utilized is used for generating an electrical output whose efficiency can be indicated using a thermal voltage efficiency. And the electrical output from a fuel cell is a DC output. Typically, for most of the electrical appliances, you need an AC output. Therefore, there is a power conversion in terms of DC to AC conversion. There is an efficiency associated with this conversion. You can also have a measure of this conversion. Then not all of the AC power that is being generated is supplied externally. Some part of the AC power is used for running pumps that is used for pumping the fuel as well as oxidants. So the power that goes towards these devices are indicated as auxiliary power. When you subtract out this power, you get the net power output to the external devices. So the entire system efficiency can be quantified based on two quantities: the net electrical power which you get, as well as the energy content of the fuel that is supplied to the fuel cell system. Let's look at it more quantitatively in terms of its subcomponents of the fuel cell system. So a generic fuel is indicated by this chemical formula. So this is just based on stoichiometry, the amount of oxygen that is used for combusting this fuel to give this amount of CO2 and this amount of H2O. So in a fuel cell, you get an electrical output, and there's an electrical work associated with that electrical output. We have already seen the meaning of this formula, delta G is equal to minus NFE. This is the electrical work that can be obtained. So we can define a system efficiency based on the electrical output divided by the free energy that is available in the fuel. So when a fuel gets combusted, a free energy release occurs. That is the value of the fuel. So in the denominator, we have the current that is generated from a fuel cell stack, the voltage that is generated from a fuel cell stack. So I times Vs would give you the electrical power output minus the auxiliary power that goes into running pumps and so on, minus other electrical losses, let's say associated wires and so on. You get the net electrical power output. We have indicated this schematically in the previous slide. In the denominator, we have this quantity. This is the mass flow rate of fuel that is input into the system, into the fuel cell system, divided by the molecular weight would give you the molar flow rate of fuel that is input into the system. This is the molar flow rate of the fuel, unutilized fuel. Delta G is the enthalpy of free energy of um, combustion associated with this reaction. Typically, when you use a fuel, you burn the fuel. From burning the fuel, you get heat. So there is an alternate way of defining efficiency based on enthalpy of combustion. The numerator remains the same. In the denominator, you have enthalpy of combustion, which can be computed using principles of chemical thermodynamics. This is the enthalpy of the fuel. You do not associate any enthalpy because with O2 because O2 is a pure component. Enthalpy of CO2 is indicated by this symbol. Enthalpy of H2O is indicated by this symbol. So in the denominator, we have the enthalpy of combustion. This is the molar mass flow rate of fuel that is being utilized. This divided by this will give you the molar flow rate. So the Vs from a stack is the voltage that can be obtained from a particular fuel cell times the number of cells that are present in the stack. Why do we use enthalpy instead of free energy here to define the thermal efficiency? Because as you know from your thermodynamics classes, delta H change in enthalpy is associated with the heat release at constant pressure. Whereas delta G is associated with work, delta H is associated with heat released. If you're unsure about these aspects of thermodynamics, you can look at another playlist I have by searching this in YouTube. This is a set of undergraduate thermodynamics lectures that clarifies some of these thermodynamics issues. Let's move on. So this is associated with this subcomponent that is defined in the following manner. Fuel that contributes to current in the fuel cell divided by the total amount of fuel that is being supplied. It is important to understand this particular term. Let's go through this slowly. Associated with 1 mole of the fuel, you have this amount of O2. But you do not keep track of O2. In a fuel cell, you keep track of current that is generated by the fuel cell, right? So if you think about O2 reduction, for 1 mole of O2 reduction, 4 moles of electrons are being utilized. So 2 electrons are used for reducing 1 oxygen atom to O2 minus. So 1 mole of O2 is associated with 4 moles of electrons. So if you multiply this term by 4, you get 4x plus y minus 2z. So I divided by this quantity gives a measure of the moles of oxygen that is being utilized for combusting 1 mole of the fuel. So the total amount of fuel that is supplied is given in the denominator. This is the mass flow rate divided by the molecular weight of the fuel. So this gives you this particular term provides a measure of the fuel that has contributed to current in the fuel cell. So take time to understand this particular term by relating this reaction to this particular term. Then you have what is called the thermal voltage efficiency indicated here, and we will clarify this term soon. So the thermal voltage efficiency is defined in this manner. So you can think through this formula in the following manner. This term, if you take it to the numerator, V times this quantity is a measure of electrical work in a way. So by combusting 1 mole of the fuel in a fuel cell, the amount of electrical work you would have obtained is the voltage of the cell times this quantity. This should be taken up here. And why do you call it thermal voltage efficiency? Because this is associated with heat release, right? As opposed to free energy of combustion, enthalpy of combustion is associated with heat release. Therefore, this term is called thermal voltage efficiency. We had already defined another efficiency in the previous lectures. That is the efficiency of the fuel cell. How did we define that? We defined that in terms of this quantity. This is associated with this quantity. V of a fuel cell is defined by the voltage generated by the fuel cell divided by the maximum voltage that can be obtained from the fuel cell. So U is associated with, let's say, open circuit voltage of the fuel cell. So that is the maximum voltage that can be obtained. We have clarified this quantity in previous lectures. Please refer to that. So we are just rewriting this using this term. Let's move on. So these two quantities are indicated here. So the efficiency associated with these two subcomponents. So this power conditioning is associated with DC to AC conversion that has certain electrical losses. So the conditioned electrical power, that is the output here, divided by the gross electrical power produced from a fuel cell stack. So that is the electrical power available here. These two can be compared in terms of eta power conversion efficiency. Then, as I said, part of that AC power is supplied to the auxiliary power. So in a way, this is being used internally by the fuel cell system. So there is typically, this is used for running mechanical pumps and so on. Therefore, we indicate the power that goes into that using eta mech, indicating eta mechanical. So that is the power that goes into the mechanical devices is indicated by auxiliary power. So when you subtract that out, you get the net electrical power. Therefore, going from here to here, you have eta fuel associated with this subcomponent. This is associated with this subcomponent. These two are associated with these subcomponents. So the overall eta thermal is dependent on all these individual efficiencies. In the next lecture, we will look at certain basic concepts associated with the stack architecture. Thank you.